All right, everyone, we are back, and we're going to talk about a really cool, basically a nest, or basically an insight that we can gather from Laplace transforms, and especially when we convert from the S domain to basically our frequency domain, and specifically the real frequency domain, j omega, where omega is just essentially your, basically your real value of your angular response, angular frequency response, or your circular frequency response, not your cyclical frequency response. But anyways, we're going to utilize this transformation to look at the frequency response of the system, specifically through what's called Bode plots. Now, once we have, and remember, the capitalization denotes we're in the S domain, that we've already basically calculate our transfer function, but now we're just basically setting that S value to your frequency response. When you have a frequency response, you're going to have a magnitude of that frequency response and then a phase lag of that response that could be introduced essentially into your system. So let's consider the following input. So let's say your control command, your input function is sinusoidal in nature. We are going to see that basically we're going to not deal a lot with these cosine. But anyways, if I have a linear time invariant system, and we're going to define this in basically the next lecture, our Laplace transform of that function will be this. And we can verify that over here. So here's my control command. This is my Laplace transform. And if we're looking at steady state, our response to that function will just be, because remember, if I have a transfer function like this, equals y of s and u of s, if I know that transfer function and I want to know what the system response is and I know my command input, I can just rearrange that, and then you see I just substitute s equals j omega, and now we're good to go here. So this would be my system response, and we can actually see that here. So if I have, and actually we're seeing here, we're not setting essentially tau here, but if this was my transfer function, h of s is s tau, and let's say tau, I just give it a value for now. This would be my y of s, and then my basically function, my y of t would be as such. So let's see how this system responds. And you can kind of see it basically symbolically illustrated here. So we set, and we've just assigned tau equal to specific value. But this would be when we transform h of s to j omega. So here, this will be the magnitude. Our phase will be this function. Now, how should the system behave at low frequency? Well, if omega is very, very, very small, what's going to happen to my magnitude? Well, my magnitude is basically going to approach 1. If my omega is very, very small on my phase lag, it should be basically a 0 phase lag, meaning no basically shift. So at time 0, if I'm looking at this cosine function here, cosine of 0 is what? 1. So if I have 0 phase lag, I should see essentially that value 1. So let's go ahead and let's see. When my omega is very, very, very small, so we can actually see, oops, let's look at this here. And now you're seeing here, I'm not taking this part and this part because that's not corresponding to the real domain. And then I could plot it here. So we can see what's the response. And this is in frequency space, or actually this is time space, excuse me. But you can kind of see, if I look here at low frequencies, the response is basically magnitude of 1. And there's no phase lag, right? I'm 0, 0. So if I do, for example, 0.01, and I can basically pull these out, and actually I can see here, actually, yeah, I can pull this out. I'm just going to plot this as such. I'm going to get rid of the parts corresponding to the non-real, although it doesn't really matter too much. You can kind of see here. So again, my magnitude is maxed out, and or basically it's equal to 1, and there's no basically like phase lag. So I'm basically still cosine compared to my original function. So that's essentially what we've got. Now, what happens if I increase the frequency dramatically? Let's say I go to 100. So now here's my response. And we can see that, and we can predict what's going to be here. If my omega increases, the H should be close to 0, and the phase lag should be close to basically minus 90. So I'm going to get rid of this again. I'm going to get rid of, oops, and then let's go ahead and let's look at it, 0.1. And let's look at it, maybe 0.05. So we can see here I'm getting close to 0, right, for my magnitude, and I'm phase lagged, right? I'm 90 degrees shifted. So this is great, but this is a lot of work. I have to solve, I have to do all these things. Instead, if I know what my transfer function is in this scenario, which was this initially, I can do and plot a Bode plot. And I can see how is my magnitude going to change as I shift from 0 to basically high values of frequency here. And again, this 0 just basically, again, it's a logarithmic scale here. And here we're essentially showing the change in frequency. So the value is decreasing. And that's kind of exactly what we see here. The phase, right, initially 0, I'm in phase, and then I'm shifting as I go to higher frequency to minus 90. So this is fantastic. I'm seeing that same type of behavior. I can do the same thing if we have this function, and we're going to see here, this is an underdamped second order system. It is our spring mass damper system, effectively. And what we'll see here is that there's some frequency where there's resonance, and you can see where the magnitude spikes, then decreases. There's basically a delta function in the phase shift. So this is characteristic of kind of your spring mass damper system. And you could observe all these behavior with Bode plots. This is particularly different, and you're kind of going to see phase shifts. You might see like decibels. So there's a lot of frequency responses, especially like in electrical engineering, when you're designing high pass, low pass filters. You can kind of see that here. Resonance control, shaping essentially loops. We're going to actually focus on this. Lead and lag compensators, we're going to design those. Stability margins, we'll design those as well. But this filter design is really, really important. A lot for electrical engineering ideas there. So that's really, really important. And then we're going to finish up this lecture with just some kind of block diagram linear algebra. And that's going to be it. That's our basis and kind of our foundation for basically control design. Next time we're going to get, and then after that, we'll get into what's a linear, an LTI system. And then we'll go ahead and start to kind of get into really some fun features and stability, and then developing our own control systems. So we'll see you next time. Thanks. Bye.